Hello everyone, my name is James Powell, and this is my PyData 2021 presentation. Today is Thursday, October 28th, and this is a pre-recorded presentation. And so, without further ado, I present to you how to be a Pandas expert. When we talk about developing expertise in a particular tool, it is generally not the case that expertise is gained through studious memorization of an API, studious memorization of details, but instead through judicious understanding, judicious discovery of what the core concepts, what the fundamental intuition is underlying these tools. When it comes to a tool like Pandas, the API is quite large. There are many different methods, there are many different data types, and there is a lot of detail. And I hope you'll see in this presentation that there is just one core concept that really brings together almost all of the Pandas API and all of these details when you look at a tool like Pandas. That core concept is the index and index alignment. Through this presentation, we'll try to motivate what the index is all about and why it's so important and why it's so intimately related to everything that's going on in Pandas, and we'll do that via some live coding. And so I will share my screen with you. I'll hide in the corner here, and we'll jump right into what we want to cover. We're going to be going through these notes in a live coded fashion, and bear in mind these notes will be available to you after we are done with this presentation in both code form and PDF form. But to get us started, let's talk about why Pandas in the first place. Why do we even bother with Pandas? Because in my opinion, Pandas is a very one-dimensional tool. There's basically only one reason to use it, and there's a pun in there too. And if you think about all the different reasons that you might have landed on using Pandas, there are a lot of reasons that might come up, but they're not very good reasons. For example, maybe you want to use Pandas because you like the Python dictionary and the Python list, and you're looking for something that's even less convenient and even more perplexing. For example, here we can see this thing called a Pandas series. And it prints out a little bit differently than the list. And we can iterate over the contents of it using iter items, but we get that like 0, 1, 2, 3, 4, the numbering of the rows. I don't know why that's useful, so maybe we'll just unpack that into a variable you don't use. Or we could iterate over this directly, but I don't really see what this is gaining us over a list. Or, more likely, if we're using Pandas, we're familiar with the Pandas data frame. And this kind of looks like maybe a dictionary of Python lists, or maybe a bunch of lists stacked next to each other, or some sort of matrix. And again, we can iterate over this thing, but when we iterate over this thing, we get something really weird. We get the column names. How is that useful to anybody? So I guess we could find iter rows, but I have no idea what this is giving me. This is giving me 1, 2, 3. Giving me it's the row and each one of the columns, or iter items. That's kind of like a dictionary, right? And this gives me each of the columns independently. I guess I can throw away the column name and then I get the columns. I don't know why somebody wants that. Or I could do iter tuples. And there I'm starting to get kind of close to something I can deal with. Tuples, lists, dictionaries, I understand those things. Because if you compare something like a Pandas data frame or a Pandas series to the built-in data types in Python, the Python list, the Python set, the Python dictionary, I'd say in terms of just straightforwardness, the built-in types really went out. Here, we have a Python list, and it's just a bunch of numbers in some structure that we can iterate over. And we can iterate over and get each of the individual numbers and do something with each of the individual numbers. Here, we have a Python dictionary, and it's just some sort of key value pairing, some labeled set of these values, and we can iterate over each of the labels, each of the keys, or we can explicitly do it with the d.keys, or we can go over each of the individual values, or we can go over the pairing of the keys and the values. That seems pretty straightforward in a very simple API. And so if we think about why we might use Pandas, clearly it's not for the strange namings of all these things, iter tuples, iter rows. Maybe it's for the really bizarre errors that come up when we use Pandas. Here we have a Pandas series. And it seems to be just a couple of numeric values. And here we have a Pandas data frame. And it seems to be 3 sequences of numeric values, 0, 1, and 2. And we can multiply these, but we get a bunch of nans on the end. How is that useful? Maybe I'm multiplying in the wrong way, kind of like matrix multiplication isn't commutative. And so here, we can see that it doesn't actually matter the direction in which I multiply these. S times df1 times s doesn't make a difference. Maybe I'll introduce another data frame into the story, and we'll see if anything else happens. So here we have a different data frame, and if I add that to the first data frame, I get a bunch of nans at the beginning. Well, that's no big deal because at least I can just drop the nans. I guess that's what I do all the time with Pandas, just drop nans because they're popping up all over the place. And what I could do is I could pretty much join these, and I get a bunch of nans there. I guess I could drop them. Let me introduce another data frame here. And this data frame doesn't look altogether too dissimilar from the second data frame we were looking at. And let me try and join these. And when I join these, it says cannot join with no overlapping index names. Hold on a second. Joining should just be like stacking them next to each other, kind of like what that plus operation seemed to be trying to do. And so why is it telling me no overlapping index names? What the heck does that even mean? And if we are unlucky enough to ask one of our coworkers, what does this mean? Why is Pandas giving me this error? They will helpfully tell us, oh, the answer is you got to rename the axis. Just rename the axis to something on both sides, and then the join will work as you expect. And you'll say, what does that even mean? How is that helpful? That's total nonsense. Rename axis? My goodness. And so if you compare that to our built-in data types like the list just makes sense. Here we have a list called x's, here we have a list called y's, and these represent some opaque collection of items that we iterate over. So if we add them together, that is some sort of sequence level operation, or rather some sort of container level operation. It concatenates them. And if we want to use some special syntax for this, we can unpack these lists into a list literal, so we can concatenate them in a different fashion. And if we actually want to add them up, lining them up, well, we just do an explicit for loop, and we can see exactly, oh, you're zipping the x's and the y's, and you're finding each one of the pairs of those values, and you're adding up those pairs. That just makes sense. There's no rename axis in this. My goodness. And the dictionary also makes a whole lot of sense. Here we have a dictionary with some key value pairings. We have another dictionary. We can use this unpacking syntax to merge these dictionaries. Yeah, merging dictionaries. You take all the key value pairings of one and all the key value pairings of the other, and there's some order of precedence for if there happens to be an overlap. And if we happen to be using Python 3.9, we can even do this with just the pipe syntax. And if we want to do some sort of arithmetic operation, then we can explicitly do that arithmetic operation. We can take the keys of one of these, put them into a set, takes the keys of the others, put them into a set, find the set union of those, and then look up the values, and then create a new dictionary with the keys and the values attained by from one side or the other. And if we don't see one of these key value pairings in one of the two sides that we're adding, we can substitute a zero value by using the dictionary.get. And even if we go into the Python standard library and look at the other collection types it provides, they just make sense. Like the collections.counter totally makes sense. It's just kind of like a dictionary, except it specifies that the values have to be some sort of integers. And so, or some sort of numeric value, some counts. And so if we have two counters like this, we can add them together. And I guess that makes sense. You add the corresponding counts. So if you have 3 A's in one and 4 A's in the other, you have 7 A's in the result. And we can even find the intersection or the unions of the counts. And we might scratch our head a little bit and say, OK, that's stretching it a bit. What does that actually mean? But it actually kind of makes sense, because if you had two bags of things that you had counted, maybe sometimes you want to say, what's the minimum that I can rely on having in either bag, or what's the maximum I can rely on having in the other bag? And if we think a little bit, these map to our intersection, our union, our pipe, and our ampersand operators. And so that doesn't quite give us a good motivation for why we might want to use Pandas. Maybe it's because Pandas is so frustrating. We end up doing a dot values all over the place just to get back to, say, a Numpy ND array, something that we know how to deal with. For example, here we have a series, and it seems to contain some numeric values, and we have a data frame, and it contains some other numeric values, and we can multiply these, and we get all nans. What is going on here? If I drop nan here, that's not going to be helpful for me at all, because oh my goodness, I'll just drop the whole thing here. OK, let me see what happens if I take this data frame that I started with and another data frame, and I add them together. Well, they seem to be about the same size, these two data frames. But when I add them together, I get all nans as well. Oh boy, this drop nan trick is not going to help me, because I'm going to have no data left over. And so instead, maybe I'll just throw away the pandas parts, just do the dot values here. And I guess I could do the same thing with my s dot values and my df1 dot values, except broadcasting error. Oh, geez. I guess even in the NumPy universe, our life isn't that easy. And if we ask our helpful coworker, they'll say, oh, you got to use a new axis. You got to add to the axis here in order to satisfy the broadcasting rules. And you say, you know, that is just not helpful. You are speaking a different language. I have no idea what you're talking about. And if it's the case that you manage to coerce this to work and you dot values your way to something that actually gives you the answer that you want, but you still want to have that data frame for whatever reason, you can always take the result and stick it back into a data frame. And so I guess that's not too bad. doesn't seem like a very compelling reason for us to use pandas. Maybe it's that in addition to that dot values, to basically run away from pandas, we can do a dot reset index to kind of stay within pandas and throw away whatever that index is, because that seems to be the source of our problems. And I guess that might be a compelling reason to use pandas, that we can just dot reset index our way to success. And so, for example, if we have a data frame that looks like this, and we want to group by that A column, and that A column happens to be unique value, so we should see exactly the same number of groups as there are rows, we can sum all the values, which in this case isn't going to do that much. It will sort by the A values. And if we can take that and, say, add it to another data frame, and that other data frame is going to look like this, well, we can see that, again, we ended up with a bunch of nan values, except for a tiny little sliver there. Drop nan, that's not going to help. But you know what? I don't have to do a dot values and make this work. I can at least reset the index on one side, and then it's giving me something that kind of looks like what I want. Or in the group by, I might be able to pass a keyword argument to tell it, don't set the index. And maybe it's because pandas is so unpredictable in terms of what it will give us when we perform an operation. You know, good tools should be guessable. We should be able to write some code and have a sense for what it's going to do before we run that line of code. Pandas doesn't seem to be the case, because even with something simple like trying to figure out how many rows I get when I do an operation with two pandas objects, I can't guess what that's going to be. Like if I have these two series, which both contain 4 values, and I sum them up, well, okay, the result has 4 values. That's not too bad. But if I swap them out with these two series, which still have 4 values, I'm getting, as a result, 6 values. What? There are 4 values and 4 values, and I'm adding them together, and I'm getting 6 values in the result. And if I swap it out with these two series that themselves also have 4 values, I get 8 values in the result? My goodness, I can't even predict how many values I'm going to get from adding these two things. That would never happen with the Python dictionary. That would never happen with the Python list. I can explicitly talk about, oh, this is how I want to combine these two structures, and I can see immediately from that code, which might be a little bit clumsy, but I can see immediately what's going on. And so this is a pretty terrible reason why we might want to use pandas, because we have very little predictability over what's going on. Well, maybe what I might want to do is just reset index myself to success here. And so maybe I'll just take this result and I'll reset index. And then I end up with something that kind of makes sense. You have to have that extra column called index. That's not very useful. So even better than reset index. I'll reset index and I'll throw away the index completely. Just throw that in the garbage. Not helpful at all. You're really not adding anything to my life. Maybe the reason that we use pandas is because it makes very weird and incomprehensible distinctions in its library. For example, if we have a data frame and we want to go into that group by, and we want to group by this column here that is no longer unique values, but actually it's only 2 values, true or false. We want to find all the places where A is true and all the places where A is false. We want to group by and do a sum. That works. But if we want to do another operation, like say the kurtosis, then that's not built into the group by. We can't do group by.curt, so we might do a group by.transform, and that seemed to give me this result, 1, 2, 8 rows? What on earth is going on here? Or maybe we'll do a dot apply, and that gives me A and B like that. That's bizarre. And maybe eventually we'll come back to doing a dot ag, and that seems to kind of give me the right thing. But why on earth did they create dot transform, dot apply, and dot ag? Why not just have one? Why not just make this easy for me? And what on earth does this even mean? Maybe it's the case that we use pandas because it is full of minor conveniences that allow us to eliminate more or less about one line of code. For example, if we have a series, we could take that series and we could shift it by one value, or we could shift it and subtract it from itself. Or we could do series.sum, or we could do series.mean, or series.skew and kurtosis. And between you and me, I don't even know what skew or kurtosis means. Sure, kurtosis is what, the scaled 4th moment of a distribution? No clue what that actually means, but I do know that I could have just imported this from scipy.stats, and I could have just used the numpy and d array, and I could have just used indexing on the numpy and d array to chop off the first element. If I'm going to drop the nan anyway, what's the difference? And I could have just done a subtraction. That seems much clearer. Do the subtraction of these elements, removing the first element from one and going up to, here this should be the last element on the other. And for the rest of these operations, .sum and .mean, already provided by numpy, and skew and kurtosis, great. I got to eliminate one scipy.stats import. Doesn't really seem like a very compelling choice or a very compelling reason for why we choose pandas. Maybe it's because we have this data frame thing in Pandas, which seems to be the ability to work with grouped data sets. And it only costs us about 250,000 lines of code of complexity in the Pandas library to have pretty much a dictionary of NumPy and D-arrays. Here is a data frame like many of the data frames that you've seen before, and I guess I can do operations down the data frame, like I could create the column sums, and I guess that would probably take me as many as 2 or 3 lines of code, maybe a dictionary comprehension if I wanted to do this in pure NumPy with a dictionary and a dictionary comprehension. And I guess I can sum across the columns, and maybe that might take me just maybe 1 more line of code. And for all of this complexity that I'm removing, group by, there's a group by in the editor tools module, isn't there? All I have to pay is 250,000 lines of additional code complexity in one of my dependencies. That's not such a high price. And by the way, 250,000 lines of code? Yeah. If we take the Pandas source code and we take every single one of the files in the Pandas directory in that source code, and we put the results into a Pandas series, after executing wc-l on that to find the length of each of those files, we can see this is every file in the Pandas source code distribution and how many lines of code are in each one of those files. And I don't care about all of those files because some of those are tests, and so maybe that's not that helpful. Maybe I'll index this thing and remove any one of these entries where it's from a testing directory or the test directory. Okay, and that gives me a mask, and I'll take that mask and I'll do a .lock operation to just pick out the files that don't belong to anything that's in that testing or test directory, and so that's what's remaining. And I'll take that result, and I'll group that result by the parent most directory and the suffix of the file. So I get something that looks like the following, where I have every file and every location, rather, and its suffix. And I'll unstack this and fill with zeros if there doesn't have to be anything, so I can get a sense for what's there. And so here I have all the .c files. Boy, that's quite a few lines of .c code. And look, pxd code, pyx code. But if I look at that .py column, 86,000 lines of code in the core and 69,000 lines of code in the libs. And if I sum this, then it'll give me the sum on, you'll see, a per file name basis or per file type basis, 194,000 lines of Python code. And if I sum this all up, I'll see this is a lot of complexity that I'm paying for. And what am I paying that complexity for? A bunch of code that makes no sense that I'm struggling with all the time does not seem like a good bet, because here's the thing. Here's my data frame, and I want to update that data frame. I do this all the time to Python lists, to Python dictionaries, to NumPy and D-arrays. So I'll do something very simple. I'll just say, go into that A column, go into the 0th row of that A column, and just multiply that value times 10. Or maybe multiply that value times 1,000 or 10,000. And it seems to work, except if my data frame seems to be very slightly different, with just one more column, I get a setting with copy warning, 250,000 lines of code, and I still have no idea what's going on. This does not seem like a compelling reason to use Pandas. And so our goal here is to try and figure out, how do we become a Pandas expert? By understanding the core concepts. And I think the core idea is understanding why we use Pandas in the first place. And so we are not here to talk about NumPy, so let's talk about NumPy. Why do we even bother with NumPy in the first place? Well, that makes sense. Python list is slow, NumPy is fast. As part of our conceit for this, here we have a simple little timer, and we'll time some code. If I sleep for 1 second, it takes a little bit more than a second to run, and you can see our timer is not a great timer, but it's approximately a decent timer. Well, if I use pure Python, my Python list that I'm familiar with, and I create 2 Python lists of size 100,000, it takes about a half a second. And if I do the same thing with the NumPy API, it takes about 100 times less. Okay, so that's a benefit. Fast code is good code. And if I take these operations and I compute their dot product, I can see it takes about 0.02 seconds to do the dot product in pure Python. I can totally understand what's going on here. Take each of the values of x's, each of the values of y's, pair them up, multiply them, and then sum the result. That's a dot product. But if I do the same thing with NumPy, you can see I get an incredible improvement in the speed. That's 70 times faster. 70 times speed up on some code. That's definitely worth it. And one of the core ideas that I have when I think about NumPy, and I try to motivate why I use NumPy, is NumPy provides us with the ability to do numeric operations faster because NumPy is a restricted computation domain. Namely, it's the ability for us to put a manager class around some sort of Python data to intermediate between the Python layer of our code and some code that has implementation, perhaps in C or Fortran. Because we have that implementation barrier, we can do things like unboxing values, make them contiguous, have exact control of memory, eliminate dynamic dispatch. And as a consequence, we're getting 100 times speedups, 80 times speedups, 70 times speedups. We're getting a significant increase in the speed of the code. And the reason that we should think of NumPy in terms of this restricted computation domain idea is it's this domain, and we have to stay inside that domain or we lose all that performance, because if I take my Python.product and I apply it to my NumPy data and I cross the boundary of that domain, it's actually slower than if I had done it in all pure Python. This restricted computation domain idea is very important because it gives us that fundamental motivation for why do we stay within NumPy? Why do we stay within Pandas? Because it is a domain which has intermediated between the pure Python level and some implementation level. As long as you stay in that implementation level, everything is fine. But if you cross that boundary, you're creating a number of additional costs that are going to be worse than if you just stayed on one side or the other of it. It's a domain which gives you certain restrictions to allow you to do computations faster. And in fact, if we think about what NumPy really is, it's really just an interpretive view of raw memory. Here we have a NumPy and D array, and we can dig into that NumPy and D array and see that this is actually raw memory at that memory location that we're interpreting in some fashion. We're saying some block of memory at this location contains int64 values. And we interpret it to be 3 values in a one-dimensional structure, just 3 values. And we have some mechanisms by which we can in constant time, move through these values, some striding mechanisms associated with these. And all of these pieces fit together when we think about NumPy. It's also that NumPy provides us with something that's missing from Python, which is a vector matrix mathematical type. In other words, if we have our Python list is some sort of opaque collection of items. So when we add 2 lists together, because they're opaque collections of items, just a bag of stuff that we iterate over, well, the addition of these 2 should just be all the stuff that we iterate over. It should just concatenate. Or if we multiply something that's a list, and it's just a bag of stuff, well, then we're just saying, oh, give me that bag of stuff 3 times over, repeat this thing. Whereas if we do the same on a NumPy and D array, we get what we expect to be mathematical operations, vector multiplication, vector addition. We're saying, oh, this is not opaque. We know what's inside this. It's numeric values. And when you add these 2 together, match them up and add them together. When you multiply this, go to each value and element-wise multiply these. Okay, that kind of makes sense. And if we think about what the Python list provides us versus what the NumPy and D array provides us, the NumPy and D array provides us with some sort of fixed size, dynamic shape, higher dimensional structure. And it is important that we talk about dimensionality because this is related to one of the core concepts that we have to understand about pandas. Namely, pandas is one-dimensional data. Even though the documentation says it's 2-dimensional data, it isn't really. It's really like aligned one-dimensional data. Well, let's think about what that means. Here we have a Python list. And a lot of people would say, oh, this is a 2-dimensional list. And the reason they'd say it's a 2-dimensional list is, well, if I want to access any one individual element, I need 2 coordinates. And so you could say 2 coordinates to access something makes it 2-dimensional. But in fact, this is not really 2-dimensional because while I can access just one row, I can't access one column natively without performing some sort of looping. There's no native first-class way to access one column. And so there are 2 coordinates for every value, but it's not a 2-dimensional list. It is a nested list. It's not that I'm providing 2 coordinates once. I'm just providing 1 coordinate that gives me a nested structure. I'm providing another coordinate. So this is 2 operations, not 1 operation. And so each layer of that list only takes 1 coordinate. It's just that this is doing 2 lookups on 2 lists. And additionally, it's a nested structure. So something like this makes total sense in Python. Here, this is a list that contains lists. And one of those lists contains lists which contains lists. And if we think about what this contains, here we can get 1 value this way and we get 1 value this way. And if we think about this, we can say, well, this doesn't have uniform dimensionality. Some of the layers of this, some of the rows of this have additional dimensions. And that doesn't make sense because when we think about the dimensionality of a structure, The dimensionality of a structure tends to be a property on the structure as a whole, and it tends to be a scalar structure. It's that everything is three-dimensional. Everything can be accessed via 3 coordinates. This is nested data. This is data where, depending on where you are in the structure, the lookup may require some number of coordinates that are different from the number of coordinates in another layer. So it's not quite a 2-dimensional structure. In fact, a Python list is never 2-dimensional data. It is always 1-dimensional data. It just has the ability to sometimes nest data. Note, this structure here, completely reasonable, completely valid Python list, no mathematical meaning, impossible to represent in Numpy. What does this even mean mathematically? This is a matrix where it's kind of sticking up one off the side of one edge, and it's nested in. It's like a hypercube in one part, but not the rest. No actual mathematical meaning. Whereas, if we think about what a Python list gives us that a NumPy and D array doesn't give us, Python list gives us the ability to update the size. It's an indirection between the actual storage of this data. So I can take a list and I can append items to the end, and it just works. And if I have 2 references to that list, both of them get updated. Whereas if I have a NumPy and D array, sure, I can do an H stack. But if I have 2 NumPy and D arrays, that H stack is not updating that NumPy and D array directly, because a NumPy and D array is a interpreted view of memory. And because it's an interpreted view of memory, it's a raw block of memory somewhere with some interpretive layer on top of it. Well, I can't just resize a raw block of memory. Who knows what might be behind it? The only thing I can do is reallocate new memory, copy things over, and if I have 2 references, then I got to keep the old one around. And so only one of these references to this NumPy and D array reflects this amendment. What we can see from this is that a NumPy and D array cannot be resized, but it can be reshaped. And if we look at these 2 NumPy and D arrays, you will see 2 completely separate blocks of memory. And so here, this gives us a very clear reasoning for why we use NumPy. NumPy gives us a fixed size dynamic shape structure, which is a nice correspondence to our Python list, which is fixed shape dynamic size. Fixed shape meaning always linear, always 1-dimensional. NumPy is a mathematical type. The Python list is some sort of container type. And NumPy gives us fast code. That's great. But we're not here to talk about NumPy. We're here to talk about pandas. So let's talk about Xarray instead, because we're definitely not here to talk about Xarray. Let's say we have some sort of real 2-dimensional data, like image data. Image data is definitely 2-dimensional because I can access any 1 pixel in that image data by 2 coordinates, and I can rotate it, and the data means the same thing. And I can look at any columnar or row slice or diagonal slice of this, and that's a meaningful operation. And the whole thing is homogeneous. This is definitely 2-dimensional data. Pictures are 2-dimensional. And you can see, if I put this into a NumPy and D array, I can access 1 individual row. I can access 1 individual column without having to have any additional mechanism. And you can think that there's many different ways for me to perform these operations, but ultimately the NumPy and D array is some way for me to take n-dimensional data, in this case 2-dimensional data, and give me the ability to operate with it. Now, the reason why I might want to introduce Xarray into the story is if I have this data, even though rotations of this data don't really change what the data is. As a human being, I want to be able to access state data like a human being. So I want to talk about the x coordinate and the y coordinate, because that's something that I want to have in my code that'll be something that people will understand. They'll be able to look at that and say, oh yeah, x equals 3 and y equals 4, and they'll be able to map that to some physical reality of where this data was actually captured. And so what I'll do is I'll take my NumPy and D array, and I'll lift it up into an Xarray data array, and I'll name the dimensions. And so now I have the exact same NumPy data, but I've said, oh, one of these dimensions is the x dimension, and one of these dimensions is the y dimension. And then I can do things like select x equals 0. That is incredibly clear what this means. Select x equals 1 and y, or x equals 0 and y equals 1, one value. And I get here an array of a single value, but that makes sense. And I can select arbitrary subsets of this, arbitrary subsquares of this, or diagonals of this. Select x equals 1 and x equals 0, and y equals 1 and y equals 0. Xarray is quite useful. It gives me the ability to access my data, to look up that data by some sort of human metadata, namely what the name of the coordinate is. And you can think, when you're using NumPy, sometimes you have to transpose things because the way in which the data was read in wasn't quite the way in which your code is going to operate on that data, and you have code that hard codes, oh, look up this axis and this axis and this axis, and you need to transpose it to make that work. But with Xarray, you can name these axes. You can name these dimensions, and so any code that you write, absent consideration of any sort of performance consequences of this, but any code that you write can just refer to those axes by name and just work irrespective of whether the data happens to be transposed or not. If I happen to have this data and it was captured on something with a coordinate system, like this is physical data that I'm capturing on some sort of detector, and that detector has tick marks, 10 inches, 15 inches, 20 inches, I can add a coordinate system as well. And that allows me to say, select my data using this coordinate system. Don't select the first data value that was captured, select the data value at 15. That is very useful. And with X-ray, I can even say, select the data at x15, y13, and if you can't find that exactly, look for the nearest value. And I can even say, select the data at x equals 15 and y from 12 to 18. And if you're missing data in between, do a linear interpolation. Incredibly useful, because somebody looking at that says, oh yeah, 15, I know exactly where I put that marker on my detector when I was capturing this particular image. Very useful. And it is the case that when we want to work in Numpy, because we want to stay within that restricted computation domain, we will sometimes invent artificial axes that do not represent certain aspects of the individual data items. For example, here we have not one file, but multiple files. And we put this into one larger structure with one additional dimension, one additional axis representing the file name that we're operating on. And one of the requirements here is that every file has to be exactly the same size. They have to be 3 by 3, and they have to have a shared coordinate system. Okay, fair enough. But every file was captured on the same coordinate system from 10 to 20 on some stepping, and I just have the file names associated with each one of these files. And that allows me to do things like, say, select x equals 15, y equals 15 from the file called a.bitmap. Oh, incredibly useful. I can actually understand what the heck this is doing. Xarray is a very useful tool if I have raw mathematical data and I want to interact with that mathematical data with some additional metadata that makes it human understandable. Namely, the dimensions and the coordinate system on those dimensions. But we're not here to talk about X-ray. We're here to talk about pandas. So why pandas? Here, I have a pandas series. And if I look deeper into a pandas series, I will see that under the covers, a pandas series has a pandas array. It has a dot array here. And this dot array is one small level of indirection from the raw values that are stored. If I go a little bit deeper in this, I can probably even pull out the NumPy values stored within, and this one level of indirection, the pandas array, this extension array idea gives me the ability to do things like masked integer values, because obviously if I have a floating point value, I can store nans to represent data's missing, but I can't quite do that in integers because there's not really an unambiguous in-band encoding for that, and so I need some sort of out-of-band encoding. I need some sort of masking mechanism. Well, the thing that we call the index, that is probably the most interesting thing about pandas, is just like that coordinate system on X-ray. It's a way for us to refer to the values. And a very common indexing that we might use is datetime indexes. This isn't just values 7, 2, 0, -5, and -4. It's 7 that I captured on the 1st of January, 2 that I captured on the 2nd of January, and so on. And if I look at this pandas series, I can see it consists of the raw mathematical data that's being stored in this pandas array and some index that helps me figure out how do I translate my human understanding of what this data or where this data is captured to where the data is actually stored in memory. And I can do things like say, oh, give me the value at the 1st of January, give me the value from the 1st of January to the end of the year, or to whatever has been captured. And that works, and it's a lot more convenient than having to do this in terms of raw matrix operations, especially if I'm working with multiple data sets, and those multiple data sets weren't captured over the same time span, but there's an overlapping time span that I want to consider. It turns out that the Pandas Index is a way that we label data in order to access it and in order to give additional meaning to manipulations that we perform on this data. And so here I have a pandas series. And you can see I've indexed it with values that appear to be some sort of measurement from -20 to 20 with some stepping associated with them. And I can say, give me the value at 0. And here this is giving me the value at label 0. I can say, give me the values from 0 up to 3. And you can see it gives me the values from the label 0 up to the label 3, which is just that value 0. Now I can look at what happens if I ask for the values from 0 up to 3 from the Pandas array. Well, the Pandas array doesn't have any indexing on it, so this is the physical values from physical locations 0 to physical location 3 versus the values from label location 0 to label location 3. So one of these gives me 3 and one of these gives me 1. Well, it turns out that one unfortunate thing about the Pandas series is that square bracket notation can be a little bit ambiguous. Because if I change this indexing very slightly, you can see if this indexing is an integer indexing, then suddenly this square bracket seems to have given me the values from physical position 0 to physical position 3, not from the label 0 to 3. And if I make this floating point values, I can see something kind of similar to what I had before. It's working on the labels again, but you can see this mismatch occurs. Now, Pandas has addressed this, and it's the case that we have an unambiguous, specific way for us to access the contents of a Pandas series. We can use .lock if we want to use the labeling, if we want to use the index, and we can use .ilock if we don't want to use the labeling, if we don't want to use the index. And you can see the .lock, because it uses the index, is going to be affected by the index. The .ilock will not be affected by the index because it doesn't use the index. And if we were to compare the .ilock rather, the accessing not using the index to the .array lookup, we'll see largely they give us something very similar. The output looks a little bit different. One of these gives us the series with the original index. The other one gives us the raw values. But in terms of what values they access the same values. There are a couple of questions might show up here. One, why does that square bracket indexing by itself act the way it does? And in a moment, you'll see why that actually makes sense. And another might be, hold on a second. This is using an interval notation when you're doing the slicing. And almost everywhere else where I see an interval notation in Python, it doesn't include the endpoint. But this seems to include the endpoint. Why on earth is this including the endpoint? If I ask for label 0 up to 3 using .lock, it gives me 4 rows. If the indexing happens to match up for that, it gives me everything up to and including 3. That's a little bit bizarre. But before we take a look at that, before we think about that, let's change our index very slightly. If we go into this structure, and we change the structure very slightly, so it's a index letters from A to D, then we can actually begin to reason about this. The .lock operation uses the index to figure out what value you want. But the index doesn't have to be numeric values, because the index doesn't have to be numeric values. It could just be labels, A, B, C, D, E. It may be the case that if we want to include the next value, we want to include that endpoint where we could have just done a +1 on the .lock on the normal slice indexing to go up to and including that point. We cannot do a +1 on any arbitrary index. This is not well defined. You can see the .lock, including the endpoint, makes total sense because the .lock is using the indexing, and the indexing is not necessarily going to have some sort of ordering associated with it, and it's not necessarily going to have some sort of successive operation. And as a consequence, the .lock has to include that endpoint. Otherwise, you would not really necessarily have a way to include that endpoint. What does +1 mean if there's a datetime index? 1 day, 1 hour, 1 minute. And if we look at our various indexing, we can see some interesting things about the various ways these indices may operate. Here, if we ask from A to the end or from A to C, depending on that index, it may give us many different things. If our index looks like this, where there's a bunch of nonsense in between, well, it'll give me all the stuff from A to the end or from A to C with that nonsense. If the A and the C are repeated, you can see it's pretty smart. It gives me from the first A to the end, or from A to C, from the very first A to the very last C. But if they're interleaved, I get this weird error, cannot get left slice bound for non-unique label. But that actually kind of makes sense. This isn't a bizarre, crazy error. This is saying you're asking for the values from A to C, but there's an AC and AC. Which A did you want? Which C did you want? Which A did you want? Which C did you want? Did you want the very first A and the very last C? That's not quite clear. And if the index is in sorted order, then there's an unambiguous choice we can have. But if the index is not in sorted order, then there may be some ambiguity here. Many of the errors that you see with pandas are actually about warning you against ambiguities which do not have well-defined semantics. And it turns out that these ambiguities can arise in different circumstances depending on the index. There are, in fact, many different types of indices that you may encounter. There are your simple range indices. And if you look at that range index and you look under the covers, you can see, well, there's a dot array, and it's just some values from 0 to 4. 0 up to and including 4. There's a range index that looks like this, and you can see it's some sort of stepping. There is an integer 64 index, and you can see that integer 64 index is just a bunch of integers that represent, this integer maps to this particular physical location. There's a datetime index, and you can see that you can have a datetime index with a set periodicity, with a set frequency, and you can even change what that frequency is. You can have an interval index that says, if you're looking for a value between 0 and 2, then this is, or between 0 and 1, between 1 and 2, between 2 and 3, or between 0 and 2, and between 2 and 4 with this particular notation for which side is closed. You have that. There's a period index. If you're looking for a value in Q1 of this year and Q2 of this year, there are all these possibilities. And this may lead you to believe, especially if you do a dot array on all these, that the index is data. But the Pandas index isn't actually data. It is something that is convertible to data. It is something that is often backed by data. But the Pandas index is actually mechanism. And here's my proof for it. If I have a range index with all the values from 0 up to 100, that's what it looks like. If I have a range index from all the values up to whatever that looks like, and this is actually data, I would run out of memory. I can't store all the values from 0 up to 1 quadrillion, up to 1 quintillion. There's no way for me to store that in memory. And yet I can create this range index. The range index is a mechanism by which we take a human description of where the data is, the label, the key, and we map it to the physical location. And you can think a range index is a very simple way, because whatever you asked for in terms of the give me the element at 24, it just gives that back out to you. Or if it's starting from a different starting point, or if it has a different stepping, it just does a little bit of arithmetic in order to figure out what the corresponding physical location would be if there happens to be some logic here. And when you look at the index has some information about itself. It knows things like whether it contains duplicates. It knows things like whether it is in sorted order and whether the values are unique. Because that's going to determine whether operations that use the index, like that .lock, are well-defined or not. The index is centered around a method that you might call, or it's centered around this method, getLock. And getLock says, I'm going to translate for you what one key turns into when you want to find the physical position. So getLock, called with 10, for this particular index says, the value 10 on a range index from 10 up to 20 stepping by 5, well, that value is going to be at 0, the position 0. This is the translation between the human description of where the data is and the physical description of where the data is in some underlying storage. And there's also operations on this like slice locks. If you say, give me all the values from 10 up to 13 with the human description of it, that's equivalent to a slice of 0 to 1 on the physical location of the data. And there's other things like getting indexers. You can give it another indexer, and it can tell you how to find these. So if you say, give me all the values from 10 to 30 stepping by 5, you can see it'll say, get the value at the 0th position, the value at the first position, and those negative ones indicate that that data is not located in the original data set. And so that's maybe why we might need to do some NaN filling for those negative 1 positions. The indices, in fact, support a bunch of common operations and a common API. And so here are a bunch of the different types of indices. And if we iterate through each one of these indices, and we take a look at whether it has a get lock, whether it's monotonic, whether it's unique, whether it has a duplicates, they all do. And if we take all of these index types, and we look at all the methods they support, minus the ones that begin with underscores, and we find the intersection of all of these, we can see there's actually a fairly large surface area for the methods that the common indices that you interact with implement. It's more than just is monotonic, there's is monotonic increasing, is monotonic decreasing. There's quite a bit that these commonly support. Unfortunately, this does make it somewhat difficult for you to create your own mechanisms for looking up your data to extend the index, especially if you want to do something a little bit unusual. Here's an attempt to do a very simple symmetric index, an index where you can say, you know what, according to my analysis, the human's description of where the data is located is invariant on whether it's on the plus side or the negative side. If I say -2, that's the same thing as asking for the element at 2. And I want all my logic to represent that so somebody can understand, it doesn't matter if you ask for the -2 element, that's the same thing as the element at 2. But I don't want to double the amount of data that I store, especially since I'm just storing redundant data. So I'll create a symmetric index. It's kind of like the Int64 index that says, if you give me a particular location that I need to look up, I'll just take the absolute value of it and give you that corresponding location. And this very simple code actually mostly works. Here's my index 1. Here's my series. You can see that's my symmetric index in place, and I can ask getLock, give me the element at 2, give me the element at -2, and it says, oh, that's corresponding to the element of position 1, and I can even do my lookups, and you can see it gives me the same value. The unfortunate thing, however, is if I had another series object and I wanted to add these together, it won't add them in index align fashion. There's a lot more mechanics that need to be done in order to make this work. See, there's a bunch of nands here, and that kind of makes sense because this series 2 had a bunch of locations which the other one didn't have, but you'd expect this one location to be filled in and this one location to be filled in, and they're not. And in fact, it turns out that it's a little bit tricky for you to create your own custom indices because there's a lot of mechanism that happens behind the scenes to make these indices work. I want to show you what happens when you do a simple S1 plus S2 operation in Pandas. And what I'm going to do is I'm going to use the sys module to set a tracer. I'm going to trace every function call and every function return. I'm going to put the results into a Pandas data frame with the file name, the line number, the name of the function, and the depth in the function call stack. And so I'll take some very simple code, like take this series here and this series here, and add them together. And let's take a look at what these two series look like. They are not that unusual. They're just two date-time index series where one of them is from the 1st of the year to the 5th of the year, and the other one is from the 2nd of the year to the 6th of the year. So they're slightly offset. Well, here, I can perform this operation, and I can look at the data frame that results from this, and let's take a look at this data frame, and there are a lot of function calls, 677 function calls that I was able to capture from just that S1 plus S2. If you look at all the function calls that are less than a depth of 5, you can see these are all the function calls that are happening. I'm doing new method, then I'm doing a bunch of checks. Okay, that kind of makes sense. Arith method, I guess that's launching me into the plus. And you can see there's quite a bit that's happening here. Ensure wrapped of datetime, like there's a lot of extra mechanism in Pandas. And if I look for all the function calls that are relative in terms of the file location to core indices, you can see there's about 155 calls into something related to the index here. And so there's quite a bit if you need to extend your own indices. And this is one area where I think Pandas could be improved, making it easier for you to extend some of these built-in structures like you're making your own custom indices. But critically, our goal here is not to extend indices to become a Pandas expert, an expert at using Pandas. And so just to get a sense of what this index is, we can think it is operative metadata. It's metadata that has well-defined semantics in terms of data operations that we use. It's metadata that's used as part of some operation. Let me show you what I mean by that. If you have a Pandas series, you can actually attach metadata to that Pandas series, like the source of this data or the author of this data using the .addrs. And this will actually be preserved through operations. So here we have two series, two data sets, and they have different sources, and they have one stored the author, and the other one stored the date when it was captured. And you can see I can look at these data sets, and I can look at what those attributes are. And I can perform a group by on one of these data sets, and if I perform that group by in some operation, you can see, oh, it appears that I have lost my metadata. Well, that's a shame. And different versions of Pandas are better and worse at, or getting better at preserving this metadata, but you can see when you do the group by, Pandas is like, I'm not quite sure to do with that metadata, and it threw it away. If I were to take these two series and I were to add them together, you can see it preserved the metadata, but it preserved the metadata of the first series. If I add them in the other direction, it preserves the metadata of the second series. And that's not something that you usually consider, oh, that the order of operations is going to affect where the metadata is. But if you really think about this, this kind of metadata has no well-defined semantics in terms of the operations of the series. In other words, if you add these two series together, what do you do with the metadata? Do you merge them? Well, if you merge them, what does that mean to merge them? If there's two sources and they're each strings with the file name, do you return a set of the two file names? Do you return a list of the two file names? Do you take the bigger of the two file names? If there are two dates, what do you do? If there are two authors, what do you do? If one of these had a numeric value, the other one had a numeric value, like number of bytes. Do you sum those? Do you put those into a list? What happens? And so in the absence of well-defined semantics in terms of this metadata, Pandas is doing the best they can do, and then the best they can do is just grab the metadata from one side or the other. Now, the metadata that we have on a Pandas series is not just the adders, but there's also a field called .name. And you can see that the .name of these two is not being propagated when I add these. Different versions of Pandas may or may not propagate the .name here. In some cases, you make it the name of one side or the other. But the core idea here is there are operations that we can perform on this Pandas series where the metadata that we have for that Pandas series, namely the attributes and the name of that series, may or may not be preserved, and it's not well defined. Whereas when we think about the Pandas Index is always well defined in terms of the operations because the operations are defined in terms of the Pandas Index. And so the Pandas Index is actually metadata that will be preserved through transformations that you perform on that data because those transformations will be defined in terms of how they change the index. And so it's some sort of persistent metadata that's very closely tied to that data. Well, if that's the case, what are the rules of the index? Well, we're here to talk about Pandas, so let's talk about Numpy. And if we talk about Numpy, we want to figure out what are the rules of Numpy. We might think, what are the rules of Numpy broadcasting? What are the rules of Numpy promotion? And so an example of trying to discover what it means to develop expertise via a look at the rules, we can say, well, if we wanted to understand NumPy, one of the things we want to do is understand what are the rules of the NumPy array. So if we have a NumPy array that looks like this, 4 values, we might be curious, what are the rules which the D type of this data set changes, where something that is integer data may turn into non-integer data. For example, if we take these values and we take the logarithm and then exponentiate them, we get floating point values back out. And it doesn't round trip back to what the original result is. And this might not seem like such a big deal. Floats, integers, doesn't matter. But if we look at these floating point values and we see, is every value in this thing equal to the first value? No, because they're all different numeric values. If we mesh grid this and see, is every value equal to every other value? No. Is every value close to every other value? No. These are 4 distinct values, 992, 993, 994, 995. But if we had some promotion happen behind the scenes and these turned into floating point values, then the first value is equal to all the other values, every value is equal to every other value, and every value is close to every other value, because as a consequence of this promotion, we lost the ability to store the distinction between these 4 values, because you can see 2 to the 53, we're probably working with IEEE 754 double precision floating point values. We don't have the ability to precisely store that last digit. And so you can see that the rules of promotion will be very important if we wanted to learn about NumPy. Now, I don't want to go into the rules of precision for NumPy, but I will say that, unfortunately, this is one area where you may want to use a tool other than Pandas, because the rules of promotion and the associated loss of precision, it's very easy for this to happen in Pandas. If we have these 2 series here that both contain the values 992 to 995, but they're differently indexed, and we ask these 2 series, do you contain the same values? They definitely do. We ask if the indices are the same. They're not. We sum these 2 values. It'll do an index-aligned sum, which will pop up nans where things are missing. As a consequence of filling that nan, well, we can't store a nan in an integer array, so it's going to promote everything into float 64. And we might say, oh, but there's a .add call, which is a fill value. So maybe I could fill with an integer 0, and it'll preserve everything in integers, but no, it won't. And so, unfortunately, Pandas will sometimes get you into that floating point D type, even if the API suggests that it might not have to. And as a consequence, this loss of precision can sometimes happen a little bit more easily in Pandas than it can in NumPy. But our goal here is not to talk about NumPy promotion operations. And it's not to talk about NumPy broadcasting, but let's talk about NumPy broadcasting, because it'll help us understand what index alignment is, this thing that we've mentioned a couple of times so far. If we think about NumPy broadcasting, it's about taking 2 dissimilarly shaped data sets and figuring out how to match them up so that an operation performed on the 2 of them makes sense. In other words, if I have x's and y's, and x's looks like this, and y's looks like this, I might say, how do I add these 2 together? Well, y's has 2 values, and x's has 2 levels, so maybe I add one of the values from one to one of the levels of the other, and one of the values on the other one to the other layer or the other level of the other one. But when I add this together, I get a broadcasting error. I cannot broadcast these operations together. And if I swap out y with something that is 2 by 3, it still complains to me, can't broadcast together. But if I do something that's 3 by 4, it works. Wait, why did you decide that a 3 by 4 against a 2 by 3 by 4 worked, but a 2 by 3 against a 2 by 3 by 4 didn't work? And if we ask our coworker, well, how do I make this work with, say, just the 2 values? They'll say, oh, use new axis. Wait, what? What the heck is new axis all about? Well, it turns out that if we understand the rules of broadcasting, all of this makes sense, and many of the errors that we might run into will Be very clear why they are the way they are, and things like new access will actually make sense. The motivation for them will be fairly clear. Note, however, when you're becoming an expert at a tool like Numpy or Pandas, it is not guaranteed that the rules will always make sense. It is not guaranteed that the rules will actually drive intuition or conceptual understanding. Because one thing that you might wonder is, I had this very nice box drawing character here, and you might say, he used a dot format. That's one of the first times I've seen him use dot format since f-string was introduced. Why on earth did he do an f-string? And I might say, well, if you take a dash value and you multiply it times 40, well, you get a line of 40, but it doesn't look that nice. If you use the Unicode box drawings line horizontal, it looks much better. If you put this into an f-string, everything works. And so here I can have an f-string with a new line before and after, but the rules of the f-string say you cannot have backslash expressions in the f-string, so I cannot write this with an f-string. I had to use the dot format. The rule here doesn't really give you a good sense of why f-string versus dot format. The rule here doesn't really give you a broader sense of anything but a restriction that came up when they were deciding how to design this feature in a corner case where when they wanted to parse f-strings and they wanted to make it possible for additional tooling to be able to syntax highlight f-strings, they just couldn't figure out how to get the backslashes to work in a consistent fashion easily and cleanly. And as a consequence, they just said, we're going to rule against this. We're going to forbid backslashes and f-strings. That rules exist doesn't necessarily mean that rules are intuitive or drive conceptual understanding. Doesn't mean they make sense. But the rules that we're going to talk about, the indexing rules, despite them having as incomprehensible errors as the syntax error, f-string expression part cannot include a backslash. Why not? Well, the broadcasting rules and the index alignment rules make a lot of sense, and why they are the way they are is something that can help you drive better conceptual, intuitive understanding of a tool like Pandas. Because here, if we focus on this rule, and these are one of the right rules to focus on, we can see how everything fits together. Here are the rules of index alignment. What you do, the rules of broadcasting. What you do is you take the dimensionality of the structures you're looking at and you align them, and you right align them. So I'm going to take each one of these things that I tried, I'm going to right align them, and then you try and match them up. And when you try and match them up, you're either looking for an exact match, so 4 against 4, or for there to be something missing. You're doing like a zip that's going in reverse, so you stop at the short of the 2, or a 1. Here, 2 by 3 by 4 against 2, these don't match. 4 doesn't match with 2. 2 by 3 by 4 against 2 by 3 doesn't match. 2 by 3 by 4 against 3 by 4, that matches. The 4 against the 4, the 3 against the 3. So it's just going to do that operation, taking that y's, and apply it to this level here twice. For that y's of 2 that I did the new axis, that new axis, or the indexing with none, same thing, is just about nesting this a little bit deeper to add one more layer to this and to have that layer be just one element, because a 2 by 2 structure is the exact same thing as a 2 by 2 by 1 by 1 by 1 by 1 by 1 structure. Well, this new axis is just my way to obey the broadcasting rules to make these things line up. In broadcasting, you right align, and then you just match up the shape. You match up these dimensions, looking either for an exact match or for one of the two to be equal to 1. And if one of the two is equal to 1, then you just broadcast against that. And so that's how broadcasting works. And you can even double check this work here. And why it's a right alignment instead of a left alignment makes sense in terms of what we know about NumPy. NumPy is an interpretive view of raw memory. And NumPy has some shape. And if you look at the shape of this thing, 2 by 3 by 4, and you look at the strides of this thing, you might say, well, the shape is how we interpret this data as a cube or a rectangular prism with 2 layers and 3 rows and 4 columns each. The strides is how we move between the values. To go from layer to layer, we skip 96 bytes. To go from row to row, we skip 32 bytes. To go from column to column, we skip 8 bytes. Because it's int64 data, of course, 8 bytes. What you can see from this strides is that the outermost of these, the rightmost of these axes, is the most tightly packed. These are the values that are most contiguous in memory. These individual column values are most contiguous in memory. Well, that's probably why you would choose the right aligning. You want to start from the things that are most contiguous in memory to the things that are least contiguous in memory, so you're not jumping around memory too much. And when you perform operations on this NumPy and D array, and you think about what an indexing does, you can understand what this indexing does in terms of the strides. When you ask for x equals 0, well, why the indexing works from the outermost to the innermost is you're you're drilling down into the data, but you always want to get the thing that's as contiguous as possible because that's going to be as fast as possible. And so that's why the broadcasting works from the right-hand side, but the indexing works from the left-hand side. And you can see this whenever you do indexing. Every time you're doing an indexing, you're just saying, oh, give me a little bit of that view of that underlying memory, and just give me this particular contiguous block. And even if you're doing the indexing and saying getting just a particular column or something, you can see that still works. You just end up skipping over more values. Well, when I take my y's and I can see my striding, you can think that this y's that has had a new axis applied to it twice over is something which just has 0 in terms of the number of values you skip. Because it turns out that you can increase the dimensionality of a NumPy and D array, paying almost no cost by just telling it, oh, you have one more dimension, you have one more axis associated with it, and that axis just contains one value, and the strides for that is just 0. You don't skip it around at all. You can even debug your broadcasting issues using broadcast2 from NumPy. You can see if I take ZS and I try and figure out how it would be turned into something that's compatible with X's, you can see, oh, it would turn into something that has 0 striding at the beginning. It's just going to repeat that thing as many times as it needs to repeat it on this particular axis. It all kind of makes sense. And so without further ado, let us talk about the rules of index alignment, because it turns out they're all about just matching things up. Now, the rules have a couple of small parts to them, but let's talk about the simplest case, where there are no duplicate values in your index. And so here I have 2 Pandas series. And the 2 series are indexed ABCD and ABCD, no duplicate values, everything matches up. And the indexes know that they're sorted, they know they're monotonic, and they know they don't contain duplicates. When you add S1 plus to S2, it just matches things up exactly. It takes the value at A and the value at A and adds that, the value at B and the value at B and adds that, the value at C and the value at C and adds that. Didn't I tell you that the collections.counter is a first-order approximation to a Pandas series? Well, it is. I mean, this is just adding up the corresponding keys to get the value with a little bit simpler of a syntax. If it's the case that these things do not line up directly, then it'll try and do the lineup as much as it possibly can, but it's going to figure out that, oh, one of these sides doesn't have A and the other side doesn't have E, whereas the collections.counter will fill in with the 0, NumPy will fill in, Pandas will fill in with a nan, and so that's why you have those nans surrounding this. It is the case that if you wanted to look at the indexing mechanism yourself, you could play with the index. So you could say, hey, index, tell me if I'm going to do an operation with you against this other index, what would happen? And you can see, oh, if these are dissimilar indices, it's going to add up the first value, the second value, and the third value, and it's going to fill in the blank for the other one. And presumably, as part of this operation, what we're going to do is we're going to do this get indexer on both sides and union the two, and that's what the result is going to be. So the result will be the consequences of this lookup of these values and this lookup of these values merged together. Now, if we look at these indexers, we can even see that the indexers have some additional behavior. We can backfill the indexers. So if we have BCDE and ABCD, we can backfill. So we can say, oh, if you're missing something, just pick the values before that. We can forward fill something. So we can say, oh, if you're BCDE and CDEF, well, just if you're missing values and this is monotonic, just fill it going forwards. And we can even look for the nearest value. So if the indices don't match exactly, you can just find the nearest value. And when you think about that and the get indexer, you can see, oh, this is a mechanism. And that mechanism has rules associated with it for how it matches these things up. And the different types of indices may have more sophisticated mechanisms than just an exact match. Index alignment is about matching things up, but it's not necessarily about an exact match. It's about how the index considers the match to be exact, whether it considers one of these methods to be the most appropriate method, the nearest match. This is why you can put actual datetime values in a Pandas index, a datetime index, and then look it up with a string. Well, the index knows how to convert the string into a datetime value and then perform that matching. Unfortunately, these different indexing mechanisms, these indexing modalities are not available on most of the operations you could perform on a Pandas series directly. You can see if you do an s1.add, you can only really specify the level and the fill value and the axis. You can't specify how to do the indexing, how to do a forward fill or backfill. But those are operations that are available on the series itself. So you first transform the series into shape, and then you let the add be a very simple thing. Or what you do is you do index operations, and then once you have the index operations, you apply them to the data. I often find that a lot of the very complex Pandas code that I write does quite a bit of work to first figure out what values I want to merge or what values I want to operate. They do index operations. And then finally, once I figured out how to whittle down to the data that I care about, then I go to the raw data and I pull it out and I perform some operation on it. The collections.counter is a first-order approximation to a Pandas series. And so you can see all of these behaviors in play. If I have two series and I match them up, or two series and I add them together, it's just like a collections.counter matching them up. If there are duplicates in the index, what would the reasonable way to match up values be? If one of these indices had two A's in it and the other one didn't, how would we match them up? Well, probably what we do is we'd match each A in the first one against each A in the second. We do a Cartesian product here. If we look at these indices, we can see one side has duplicates and the other side does not. And so how do you match things up? There's duplicates on one side. Well, you match one of the things on one side to every one of the things on the other side. That's why there were more rows in that previous example, because it was doing the Cartesian product of the places where there were duplicates. And because the index knows it has duplicates, it'll use that as part of this operation. You can see A3, A negative 3. Well, that's because you match the A7 in the first one against the A negative 4 and the A negative 10. Index alignment also performs this Cartesian product. And if it's the case that there are duplicates on both sides, well, then you're just going to do the Cartesian product of every place you see duplicates. If there's two A's on one side and two A's on the other side, then you're going to get 4 values in the result for that A, because you're going to match every one of one against every one of the other. And that's the reasonable way to match things up. Because if you collected some data and you said, I collected this data labeled A, and I collected 2 measurements for label A on one side of the data set, and I collected 2 labeled measurements A on the other data set, I probably want to pair them up in all the different possible combinations. And if I didn't want to do that, I probably would have used unique labels. Your choice of whether these labels are unique or not is you telling Pandas, consider these to be the same conceptual entity, and so please perform the Cartesian product. It's not that this is an obscure thing that Pandas has done to confuse you. It's that you've asked Pandas to do the wrong thing by telling Pandas something that's not quite correct about the metadata related to your data. Remember, and it is critical to understand this, the Pandas index is not like a primary key. It is not guaranteed to be unique. It is not guaranteed to be sorted. It is just some mechanism for looking up the data. Dead stop, it is just some mechanism. And in fact, non-unique, non-sorted indices come up all the time. Let me show you an example of a non-unique index. Here we have a series, and that series is on a time index. It's on a datetime index. And you can see I have captured these on different disuniform measurements down to the second, from the 1st of the month to the 22nd of the month. Now, for my purposes, I might want to resample this. So I might want to resample this in terms of every minute. And so here you can see I have every minute, and everything's been rounded nicely, and I have one row corresponding to every minute. And there's a bunch of nans here because I don't have enough measurements for every single minute. There's just too many missing measurements. This is not too different from the idea of grouping these values by those times rounded to the minute and then performing the mean as well. And if we were curious about what the difference between this resample and this group by might be, we could do a little bit of index mathematics, a little bit of index manipulation to figure out what that would be. We could take the first operation that we've resampled on 1 minute intervals, and we could take every value and put them into a set. But not the values themselves, maybe the index contents, and put them into a set. And so here you can see for this resampling, that is the original data sample that at that particular index value, at 2 seconds past the minute, that got bucketed into 51 minutes past the hour. And I could do the same thing on my group by. And you can see where they don't match up is going to be the cases where this dot group by with the rounded time series is going to be different than the resample. And in fact, I could take these 2 results and I could put them into a data frame. And here you can see this data frame is a collection of like-indexed one-dimensional series. So this data frame contains all of the measurements from the original data set that correspond to 51 minutes past the hour for the resample case and for the group by case. And so you can see for that resample and that group by case, the actual value should be the same because I'm performing the mean on the same values. But anywhere where these differ, it's going to be different. In the resample case, you can see the resample is giving me entries for every uniform minute, whereas the group by is giving me no values if I didn't have anything to measure. So the group by says nan here and doesn't have any values in the result, whereas the resample will just have a NAM value because there weren't any values to perform a mean on. If I take this result and I look for all the places where they are in common, you can see these are all the places where the group by and the resample matched up in terms of the signals that they were going to compute as part of the mean. If I take that and I capture the index of this result all by itself, then I can index this thing where it's true, and I can see these are all the samples where things matched up. So these are all the places in the result where things matched up. I can take that and I compute what the same indices are. I can look up the resample and the group by where the same index are and then see if they're all matching up exactly as I said. Anywhere where they grouped on the same values, anywhere where they joined the same number of values together in that mean, they should be the exact same value. So that gives me the common index. If I want the different index, I can do another index operation. I can take the original indices of everything that they both have, subtract out everywhere where they're different, and I can see all the places where they differ. And what you can see here is index mathematics come up pretty commonly. It's the case that anytime you have a very large data set and you're working with another data set and you've captured this metadata, it's not uncommon for you to do these index operations to say, okay, take this data and then subset it and subset and subset it. And if you're not using the index, you're probably doing this on the raw data, so you're making lots of copies of the raw data, which may have many, many, many columns. And so that could be a very expensive copy. And it's probably many lines of code with lots of for loops that nobody can make heads or tails of. But here, what I'm saying is, take these two structures, figure out what samples were included in each bucket, find all the buckets where they're the same, and then compute all the places where you use the same bucket, compute all the places where you use a different bucket, and then actually go up and look in the original data to find what the corresponding calculation was for those buckets and verify that the group by and the resample are sometimes the same in some places and sometimes different in the other places, but the only difference there is how they bucketed, how they performed this windowing operation. If you think beyond the Pandas series, because we often don't use the Pandas series directly. If we're not that familiar with Pandas, we'll often just use a data frame all the time. But it turns out the Pandas series is a very useful tool all by itself. Well, here is an example of a Pandas data frame. And a Pandas data frame that you may have worked with before. It has dates, it has dickers, it has prices, it has volumes. And we can do operations like do a dot lock. Give me the element at the label 0 and the ticker column. You can do a dot ilock. Give me the element at position 0 and column 0. So I guess that would be the date. Give me the element at label 0. Oh, maybe that's why when I had the series with the square bracket indexing, sometimes there was some ambiguity. Because when you look at something like a data frame and you perform an operation on that data frame, you're going to get a row or a column. And if that's a single row and a single column, it's going to be a Pandas series. And if it's a Pandas series, you're going to want to do another lookup on that, maybe a square bracket lookup. And what are you most likely to do? You're most likely to have string named columns. And so you're most likely to want to operate on the labeling for the subsequent operations that you perform once you do the lookup in the data frame to reduce that to a series, and you want to do an operation on the series. And if you look at these .lock and .ilock operations, you can see there's quite a few of these. You can see this gave us a series object, so that's why it had this implicit behavior. It's just trying to guess what's most common because nobody really wants to do .lock like this, even though that's less ambiguous. And you can see that .lock even has the ability to have two parameters. You can say, give me everything for the ticker column and for every particular row. Now, let me remind you, Pandas is very one-dimensional. The main reason to use it is the index, and it's very one-dimensional. It only stores one-dimensional data. A Pandas series is a one-dimensional data set that has one index. A data frame is doubly indexed. What a Pandas data frame is, you've collected multiple measurements. Those measurements are collected with the same metadata, the same indexing mechanism. You want to store them together and line them up. And as part of storing them together and lining them up, you also want to refer to those measurements by another index. A data frame is a doubly indexed structure where it contains like-indexed one-dimensional data. Pandas is only one-dimensional data. Yes, the Pandas documentation calls it two-dimensional data because there are two coordinates for a .lock or a .ilock for accessing something, But if we try and compare a Pandas data frame, like the data frame here, to our X-array data, and we said the X-array data was clearly two-dimensional data, this is not really two-dimensional data because I can only look down the rows or down the columns to perform a meaningful operation. I cannot look down the diagonals. Yes, I can access this data via two coordinates, but this data is not homogeneous. If I perform an arbitrary rotation of this data, the data fundamentally changes what it means, whereas with an image, it doesn't really fundamentally change what it means. It just means you're tilting your head a little bit sideways. This is actually 4 data sets that I've collected: the date, the ticker, the price, and the volume. And I've collected this data with the same indexing. And in fact, date and ticker, that's not data. That's not something that I collected. That's a labeling. What I really should do with this data set is I should have indexed it on the date and the ticker. It's 2 data sets I've collected: one price, one volume, and I've collected them with the same date and ticker, and I want to line them up. And I want to perform operations making use of those being lined up. Operations not only on this data frame itself, but operations combining this data frame with others. This is what a Pandas data frame is all about, and this is what Pandas is all about: indexed one-dimensional data. Whether it is one indexed one-dimensional data set, a Pandas series, or a collection of like-indexed one-dimensional data, a data frame, that's what Pandas is all about. Let us take a look. Here I have a data frame, and you can see this data frame, if I access one of these rows using .lock, it gives me a row. It gives me this row as a Pandas series. If I access one column of this, it gives me a column of this. If I look at what that column is, it's a series. A Pandas series is not a row or a column of a Pandas data frame. A Pandas series is just a one-dimensional data set. When you go into a Pandas data frame and you ask for a subset of that Pandas data frame, and that subset of that Pandas data frame happens to be one-dimensional, you get a series back. That's the relationship between a Pandas series and a Pandas data frame. One is for collections of like like-indexed one-dimensional data, and the other one is just one like-indexed or one indexed one-dimensional data. And for the data frame, if you're collecting these together, you put one more index to just be able to refer to what those individual items are. Let me show you something that happens quite often in Pandas. Here, if I look up the element at location 0 and location 2, because I'm using .lock, this is going to be index aware. So if I change what the indexing is, it is going to change what the result is. A .lock operation is not guaranteed to give you a series or a data frame unless you are absolutely certain what the contents of that index is. Because if there are repeated values in that index, the .lock is going to give you 2 rows, the 2 rows where this data is set to 0, and it gives you a data frame. Whereas if you ask for entry 2, there's only 1 entry, there's no duplicates for 2, it only gives you 1. The .lock operation can give you anything. It can give you a data frame, give you a series. I guess those are the 2 options, but it can give you either one of those 2 options, and you need to understand what the indexing is in order to make that work. Where .ilock is helpful, and where .ilock is a very useful tool, even if you often think about your data in terms of this metadata, this indexing, is the ilock is unambiguous. It always represents the physical position. So ilock of 0 always means physical position 0, and there can't be 2 physical positions 0. That is unique. The .ilock can be thought of as an indexing with a range index, a unique range index starting from 0 up to the size of the structure. That's what .ilock really is. Now, when you do these operations, like you ask a Pandas data frame for one column or one row, one of the things you can see is that the indexing of this will correspond to the corresponding indexing on their side. So in other words, if the original data frame was index 011 on the columns and 00112 on the rows, and I ask for row 0, the indexing of the result is going to take the column indexing. This is why it's doubly indexed. So when you look at a particular slice down a row or down a column, you know how to index the result of that using the column index if you looked at a row, or using the row index if you looked at a column. And you can see the name of this Pandas series is set to the value of the index that you operated on to get this particular data set. So if I look for entry 2, the name here will be set to 2, and the index will be set to whatever the corresponding columns were for that. And you'll see this irrespective of whether you look at a column or a row. And so now it kind of makes sense why it is that we have this implicit behavior. This implicit behavior on the Pandas series with the square bracket all by itself is basically trying to guess what it thinks you're trying to do when you do these chained operations. Do you really want to look at the column names? Do you really want to look at the row names? And depending on the circumstances, you may want one or the other, and sometimes this works, sometimes it doesn't. But of course, you can always just .ilock or .lock your way into explicitness. The setting with copy warning actually makes sense. Consider this. If you have a Pandas data frame and you ask that Pandas data frame for one row, because this is not two-dimensional data, but multiple data sets that are like indexed, there is no guarantee that those columns contain the same type of data. Meaning, the result that you get out of this retrieval of one row is going to be a Pandas series with potentially an object D type. Because here, this row contained a string, a float, and an int. How do I store that contiguously? Well, I have to use the object D type. I can't store these as int64s because what do I do with the float? What do I do with the string? If you're doing that, and the Pandas series is built on top of, say, a Numpy and D array, and the Numpy and D array wants these to be contiguous, then this lookup is going to make a copy. It's going to copy this series, or it's going to create a series backed by some new data, and that new data is going to be the Python PyObject pointer values, the reference values for these underlying entities in memory. And it may even make a copy to bring these back into the boxed universe, depending on what needs to be done here. But whatever the case is, here, a copy is being made. You looked up a row, and it had to make a copy because this row contained non-homogeneous data, and it had to do something in order to represent this. And because it had to do that, and because it had to make a copy, if you try and do a setting on that copy, that setting might fail. Because that setting is going to change the copy, not change the original data. And the addition of that additional column in the previous example that changed this from everything working to everything failing with that can't set or setting with copy warning was because in one of those cases, I had only integer data. Because I only had integer data, the series didn't have to make a copy because I could just get a series with integers in them. Here, because this is heterogeneous data, I have to make a copy, and this is why that warning happens. And so the solution to this is pretty clear. Don't make a copy. And that's why that .ilock happens to have the ability to take two different dimensions, two different coordinates. Here, this is to allow you to say, give me the value at 0 on the positions for the rows, and C on the position for the column. Oh, wait, that doesn't work. Give me the value at 0 on the label for the rows, and C on the labels for the columns. OK, that worked. Or give me the element at 0 on the positions for the rows, and at the position for wherever the C occurred in the columns using getLock. You can see direct use of the index here, or vice versa. Unfortunately, this .lock and .getLock, this .ilock and .lock operator do not allow you to mix and match whether you use labeled or positional indexing, which is oftentimes why people do the multi-stage indexing. But in these cases, what you might need to do is you might need to actually use the index directly in order to figure out where that element is, so you can consistently use .lock or .ilock with just positions or just labels. So if we think about a Pandas data frame, and we think about what this thing really is, a Pandas data frame is typified by the block manager data that it contains, the actual data in this thing. In this case, a couple of integers, a couple of floating point values, and a couple of string values. That block manager is a topic for another day. It is very complex how it works, and it can be very opaque in terms of its operation. Closer to the surface, however, we have the index, which is our way to refer to the rows of this structure, and the columns, which is another way to refer to the rows of the structure, and these are both indices. Sometimes people call the index the row index or the major axis. Sometimes people call the columns the column index or the minor axis. Columns index can be somewhat misleading, in part because they're both index objects. They're both mechanisms by which we can refer to the underlying data. And everything just kind of makes sense when you see how the index works. And so let's wrap up our discussion of the rules of index alignment by talking about what the rules of the index alignment are on this structure that we commonly use, the data frame. If we happen to have two Pandas data frames, and they both look like this, and these are doubly indexed collections of like-indexed one-dimensional data, what we can think is, if we perform an operation on these together, it's going to match things up on both the rows and the columns index. It's going to match up from the 1st to the 5th of the year and from the 2nd to the 6th of the year on that row index. So I'll get nans at the top and nans at the bottom because I'm missing one row for one of these and missing one row for the other. And since the columns are the same, it's just going to match those columns up by name. And that's exactly what I expect. If there is an extra column in one, then I'm going to get all nan values because it's going to match things up on both of these indices. What are the rules for combining a series with a data frame? Well, when you have a Pandas data frame that looks like this, and you have a Pandas series that looks like this, it's going to match the columns of the data frame against the rows of the series. And notice, even though it should make sense to you, oh yeah, you're just going to take that series and you're just going to take that 42018 and just multiply them across, that's not actually what happens. When I perform this, it gives me a weird result with a bunch of nans because it took the row index of that series and it tried to match it against the columns. And because the row index of series and the column didn't match up, I just get a bunch of data, all nans. And it doesn't matter the order in which I perform this operation. It always matches the rows of the series against the columns of the index. And I can't transpose my way out of this, by the way, because a Pandas series is not something that can be transposed. It's not a column vector or a row vector. It's just a one-dimensional data set. So it has no notion of what its orientation is. The transposition of a Pandas series is just the series itself. And so there is no way for me to transpose my way around this. But this actually makes sense why this rule is in place if you think about how we actually use Pandas series and we think about the operations we actually perform. And so if we take a look at these two structures, here I have a series that matches the column indexing of the data frame. Then I can add these together, and I can immediately see how this is useful if I go back to my real-ish world data. Going back to my real-world data, here is my data frame containing dates, tickers, prices, and volumes. I've already set the index of the date and the ticker. I have some factors, and this is indexed by the ticker. So for each one of these tickers, I have some multiplicative factor that I want to take this original data, and I want to multiply it through by. If you think about it, that multiplicative factor is unlikely to affect both the price and the volume. If you think this is maybe even an additive factor, it makes even more sense why it's unlikely to affect both. The price can't be negative, but the volume can. The volume is integer data, and the price is floating point data. So it's unlikely for that factor to apply to both of these. It's more likely for this factor to apply to just one of these columns. And so what I'm likely to do is I'm likely to take the data frame, pull out the one column that I want, which gives me a Pandas series, and do a series-based alignment here. That makes sense. Or what I'm likely to do is take two data frames that have the factors for the prices and the factors for the volumes and apply those data frame by data frame, matching up the columns on one column against the other, the rows on one, the rows against the other. If I mismatch them, then what it's thinking is what I want to do is I want to match up the columns. I want to do something to all the prices and something to all the factors, moving down that data frame. Because most of the operations that you can see are performed on a Pandas series or a Pandas data frame tend to be performed down the data frame, down the series, down the rows of this structure. Now, you can see here, this is a multi-index structure. So I can do things like index slice this data frame to get all the places where I'm looking at ticker ARNQ. And this index aligned operation is aware of that. So even though I have all of these prices, and this is indexed by this multi-index of the date and the ticker, and I have this factor that only includes the ticker, Pandas is smart enough to figure out, match each one of those against every one of those dates. Think about how much pure Python code, how much looping code it would take for you to make that work in the same fashion. So what is this multi-index? And what are the alignment rules? Well, the alignment rules are pretty straightforward. The exact same alignment rules that you see on the series and the data frame. It's just that Pandas is able to use the name of the index levels in order to figure out how these things match up. And this is why you sometimes get these errors around, oh, this is misnamed. This is why you can see I always set the name of my series, I set the name of my indices. That's what Pandas is using. That's the metadata that Pandas uses to figure out how to do the matching. Let me show you a series with a multi-index. Here's a series with a bunch of symbols and a bunch of quarters that I've collected this data from. If I look at this, I can see this is clearly a multi-index. If I do a lock operation, I can see this is hierarchical, so I can look at everything for Q1, or I can drill down and I look at everything for Q1 and ABC. You can see if I did this with another index, so if this were a data frame and I had another coordinate here representing the column that I'm looking for, is this one-dimensional? Is this two-dimensional? Is this like nested one-dimensional? You can see why the multi-index definitely makes this not really our sense of one-dimensional, because there's two coordinates that are used for one and one coordinate used for the other, but they're not splatted. This is nonsensical because this would be a three-dimensional data set. Pandas data frame isn't really two-dimensional. It's actually like indexed one-dimensional data. But here you can see I can drill down. And I can even use index slice to do really smart cross sections, like give me the ABC and the XYZ for Q1 2021. And because it's a very smart index, I can even give it an actual date, like the 15th of March forward, and it figures out which quarters are going to be affected and then does a slice on those to give me the corresponding tickers. And the index alignment here is just smart, and it figures out what layers match up to what layers and does the index alignment on those layers. Note, multi-index is a topic for another day, and it is a very big topic. People are often afraid of the multi-index, especially if they don't like using the index itself, because it has these weird hierarchical behaviors. But the multi-index is not the only hierarchical index, because it turns out, because that index is just a mechanism, hierarchical indices pop up all the time. A date-time index is hierarchical. If you ask for just the year, they'll give you all the rows for that year, just like if you had asked the multi-index for just one layer of that index. And there's a drill down that's possible with the date-time index, just like the drill down that's possible with the multi-index. It's just that the syntax for it is very slightly different, because where the different layers are being separated is once this date-time is parsed by the date-time index, or in terms of what input that I give to the multi-index. But largely these are, if you think about it, a date-time index is actually a multi-index where each level is each fidelity of time measurement that you have, year, month, day, and so forth, as deep as you happen to have fidelity. And so this is actually a multi-index with 3 levels, or conceptually equivalent to a multi-index with 3 levels, year, month, and day. It's just storing that as one particular index without some of the syntax of the multi-index. And so if we take all of this and we try and figure out indices, are they useful? Very. Indices, do we need to understand how they work and do we need to use them ourselves? Yes. Indices and index alignment. If we think about indices and index alignment and think about how they work, can we become a Pandas expert? Yes. Because it turns out that almost everything that you can do on a Pandas series or a Pandas data frame can be determined or discussed or defined in terms of operations on that index. For example, here is a series. It is indexed on individual days. I can group it by month and I can do a mean. But you can see I get an index that's the month number. That's not probably what I want. What I can do is I can have the group by. I can operate on that index and turn this into period and do that group by. And then with this result, I have a nicer index, so I can look up exact dates and have those exact dates translate to the months and have everything work nicely. This is way easier than just doing a group by index month. And then I'm basically back to something akin to my range index, because I have to figure out how to map actual dates to months, whereas I could have let the index do this myself. All the different operations that I can do in the group by make sense in terms of the index. If I have a structure and I want to group it by something, and I want the result to reflect indexing based on the groups. I want whatever my groups to become the new index. That is .ag. What .ag is about is taking the groups and collapsing them to one scalar value so you can produce as the end result something that is indexed on each of the groups, and there's one value for each of those, which is whatever user-defined function you've provided. So here you can see ag with the skew or ag with the kurtosis. Transform is about preserving the original indexing. So what transform is about is saying take some structure with some indexing, perform some transformation on it, but keep what the original indexing looked like. And so the UDF that's passed to transform should preserve that indexing. So I can't use kurtosis or skew because those are reductions. Those will collapse. But I could use something like z-score. And you can see here the z-score did what I wanted. Apply is about saying, you know what? I don't want either of those. I want a brand new indexing. Apply is about doing any operation that can result in any new index and then concatenating these back into a Pandas data frame later. And so if I wanted to group these by their month, and then I wanted to take all the positive values and find the cumulative sum, well, that's going to drop rows. So the resulting index is neither going to be just the groups, nor is it going to be the original index. It's going to have the original index with pieces missing. I have to use apply. And when you look at the result of apply, you can see it tacks the indexing that was created by the UDF here onto the indexing that is implied by the grouping, because you kind of want to know, oh, these were the dates that I grouped together to form this. And this is a main case where you might want to drop one of these levels. You might want to do a little bit of reset index just to throw away part that you do or do not care about. But that's what apply is all about. There is one more additional dimension to this, which is that aggregate and transform work on a series basis and apply works on a data frame basis. But unfortunately, we're not here to talk about rolling functions. We're here to talk about the index, and so we'll have to leave that for a future presentation. If we look at about 80% of the Pandas data frame API, almost all of these operations can be thought of in terms of something related to the index. Here is our data frame with our time series data. And I'm going to talk about as much of the Pandas API as I can fit. There's some parts of the Pandas API I won't talk about. I won't talk about things like ndim and shape, the number of dimensions and the shape of this thing. The number of dimensions of a Pandas data frame is always 2. The number of dimensions of a Pandas series is always 1. The shape is always the number of rows and 2, or the number of rows or the number of entries and 1. Not particularly interesting. I'm not going to talk about things like the metadata, like the flags and the attributes. Not that interesting. I'm not going to talk about the index, the columns, and the axes. The axes, that's just the index and the columns in a tuple. Not that interesting. I want to talk about operations like stack and unstack. Here's what unstack is. Unstack is taking a layer of a multi-index and pivoting it up into a layer of the columns. So you can see you take the innermost layer of the multi-index on the rows, and you pivot up to be the innermost layer of the multi-index on the columns. Why you might do this is because if you were to do matplotlib plotting directly from Pandas, each column usually produces an independent graph. And so sometimes here you might want to have one line for each ticker for each price and each volume. Is this useful from an analytical perspective? Maybe, maybe not, but definitely from a plotting perspective, unstack and then you plot this and you get one of these per ticker. Stack is just the opposite operation. It's just taking one layer of that column index and pivoting it down into one layer, the outermost layer of, or the innermost layer, I should say, of this row index. So there you go. Is this useful? In this particular case, probably not, because most operations you perform on a Pandas data frame are down the rows. And I don't know what operation you could perform on prices and volumes together. That's not clear to me. And so here, that's probably not particularly useful. But you can think as duals. There may be a case where you want to take something and stack it or unstack it. In general, these are useful operations. Things like melt and pivot. If you look at a different data frame that looks like this data frame is something that maybe might have been read from an Excel file. Because you can imagine how somebody put this in Excel. Each row corresponded to one ticker, and they have some sectors associated with them, and they have the dates where they captured some measurement. And when you look at that, you say, okay, that kind of makes sense. Well, what I want to do is I want to operate on this in a consistent fashion. I actually want to take part of that column index, and I want to take that and pull it down into the data. That's what melt is all about. Melt is all about saying, take part of my columns, namely everything but the sector column, and move it down into my data. And so here you can see the column labels are this variable column, and the corresponding values of this value column. And it's a very bizarre set of names, because you can see there's like var name, and you can name what these columns are. If you don't ignore the index, you preserve the original indexing. And if you set the ID vars, you actually duplicate any variables that are supposed to be identifier variables. This is actually 2 data sets that has been stored in the same structure. But here you can see, oh, OK, each date, each sector, each value. And here, probably what I want to do is I want to set the index here into this thing and sort the index. So now I have each ticker, each date in the index, and I probably even want to swap the levels of these. So it's date, ticker, and then the sector, and then that, and I probably want to sort the index on this. So here's what my result looks like. Now, if we think about melt in that fashion, pivot is kind of a dual of melt. And when you think about something like pivot, again, you can think about this in terms of operations performed on the index. The pivot is just about doing some sort of group by and then an unstack. So if I took these values and I wanted to group them by the month in which these values occurred for the original data frame, I wanted to group these by the month in which the values occurred. And then I wanted to take the sum of these values for the month. And then I wanted to unstack this. Here you can see I'm doing some sort of pivoting operation to take whatever is in the outermost layer of the row index and move it up into the innermost layer of the row index and move it up to the innermost layer of the column index. Well, a group by unstack is basically a pivot table operation. A pivot table operation is just you explicitly saying, what do I want the index to look like? What do I want the column index to look like? And how do I want to compute what the cell values are? And so here, I'm going to pivot this by saying, oh, I want as my index to be the dates by month. I want as the columns to be whatever was in that original index layer or column called ticker. And I want the aggregation function to be the sum of everything that managed to match up. That's all pivot table is. It's just an operation where you set what the columns are and we set the indexes. Sort index, obviously, sort by the index. You can sort by the index on either axis. This is just going to alphabetize either in ascending or descending order what your columns are, because it's just going to sort on that column index, and this column index is just strings. Why does sort index use ascending equals true and false instead of reverse like the sorted function in Python? I don't know. I mean, there's cases where the Pandas API diverges from what we might expect. This is probably influenced by some non-Python tool. I can sort by values. OK, that's pretty obvious. Reset index, what reset index does is it takes a layer of the index and it pops it into the data. Is that useful? Well, in some cases, you do want to throw away the index. Or in some cases, you may have preserved the index as a metadata deep into an operation. And at that layer, you know that that index only contains one value. And so it's no longer valuable to have that index anymore. As part of some sort of subsetting, you have all of just the same ticker. Maybe you did a group by and you're doing some sort of nested group by. Pop off the index. You don't need it to be percolated back up if you did like a group by apply. You can drop this as well. And set index is basically the dual of resetting. It says take a column, take the data, and move it into the index. All of these operations are just moving things around, either from the column index to the row index, from the data to the index, from the index to the data. Here you can say set the index and append it. I'll just set it as an extra level. Drop level, that's just about dropping one level of the index. Take off the part of the index that has ticker in it and drop it by name. And that's why naming these makes sense. Reindex just says take the data set and don't change what's in the index. Change what the data is based off a new index. Look up new things. Reindex says here, you have your data with your indexing. Give me a new structure and look up all the values using this index to look them up. So reindex here is just saying, oh, give me all the values from the 1st of February every 14 days. And for 4 periods. So that should be up until about mid-March. That's all reindex is. Set axis, very strangely named, but set axis is about setting the values of the index given some mapper or some values itself. Given the actual values itself. So set index, taking the columns and then uppercasing them or title casing them and setting this axis the columns. This is just setting the values of the index. Mutating the index, what the index contains, presuming that the index is backed by some data. What this would do for a non-data backed index might be ambiguous. I'm not sure what this will end up calling. I think this will actually end up trying to do set item operations on the index. And so how the index is going to intermediate that and figure out what to do is up to the index mechanics itself. And so this is where the index API can be a little bit large. And this is a case where, maybe this has increased the size of the API for the index. You know what rename does? All it does is it renames. All it does is it renames the values of, it sets the values of one of the two indices, the column index or the row index, using a mapper. It's basically set index, but not using the data, using a mapper instead. So here you can see, instead of actually performing the computation to title case all of these, I can just give it a function to title case all of these myself. And so what rename could be used for is, if I didn't want to do this on the columns, I want to do this on the rows. Maybe I want to do a uniform transformation to part of this index. I want to take that date and I want to push it forward or push it back one day. I could do a rename on this. And you can see this pulled everything back one day. Just went to every one of those values and then performed an operation on them. Swap level just swaps the level of the index. Reorder levels just reorders the level of the index, given some ordering. Rename axis just renames what the axis is called. Not the contents of that axis, but what that axis is called. Because if you look at the dot columns, this dot columns is an index. It has a name field. As you do stack and unstack operations, that name field is going to be used to figure out what to name things. When you pull something from a layer of the column index into the row index, and we did that with our previous stack operation, you can see it was missing, there was a blank there because it wasn't named originally. So rename axis is about naming these. And it's valuable to name these so that when you do multi-indexed index alignment, Pandas knows how to match things up. That's why that rename axis came up before. Pandas didn't know how to match things up, so you named the layers of that multi-index in the previous example. And so Pandas said, oh, now I know what matches up, index alignment, and you're off to the races. And you see that. When you stack this thing and you look at the index, you can see, oh, this layer of the index didn't have a name because I hadn't named it. That's all it is all about. Swap axis is just about transposing this. I don't really understand why swap axis exists in addition to transpose. Sometimes the Pandas API isn't always clear. There may be some use case for swap axis that's not the same as transpose. Squeeze is just about taking something that possibly could be a series, but is currently a data frame, and dropping it to a series. It doesn't force something into a series. And so here you can see it didn't do anything to my data frame, but if my data frame happened to be just one column, Squeeze said, you know what? I'm just going to make this a series, and notice what happened to the name. The name was whatever the name of the original column was. And so this is where Squeeze comes up. And you can squeeze on either axis if you want. You can squeeze on the index or squeeze on the columns. Explode is the opposite. Explode is not quite the opposite. Explode is the idea that one of the values in your data might be some sort of nested information, like, say, a list as a consequence of how you read this in. Maybe it was like a CSV file where each CSV entry had some sub-entries. Explode just says explode them. And notice it explodes it down the rows. And notice how it preserves the indexing. See, duplicated values in an index come all the time. You can see the 7 was attached to the 3 was attached to the 0. It's just exploding something nested into additional rows. Common operations like at and iat and lock and ilock, just about accessing things. What you can think is if you do an iat, and for that iat, we're missing a pair of parentheses here, you try and access. Oh, and this should be square brackets. Here, if you do an iat, you can access a single value, or an at, you can access a single value. You can either access a single value by its label or access a single value by its position. Very similar to .lock and ilock. The one tiny difference between these is these will always give you the scalar values, whereas a .lock is going to give you, potentially, a series, a data frame. It'll give you a Panda structure back, whereas the ilock may give you just a single value. Other operations, .head, it's basically just like an ilock, giving me the first 3 entries, or giving me the first n entries. A tail, it's just like an ilock, giving me the last 3 entries. It's just an index, not aware operation. Sample is just like an ilock's, giving me some random choice of values. All of the binary operators, like .add, index aligned. They take the index from one, the index from another, and they add them up. And here I'm adding this to itself, and so obviously it'll be index aligned already. Sub is the same. Subtract is just because people don't want to write subtract, and so they write sub instead, but some people really want to be very clear that this is about subtraction, not about submarines. Mul and multiply, same thing, index-aligned operations. Div, divide, also about index-aligned operations. Because Pandas is built on a NumPy and D array, which is a restricted computation domain and a raw view of interpreted, or an interpreted view of raw memory, the division scenario that we had in Python 2, where there was a difference between dividing two floats and two ints, reoccurs in the NumPy and Pandas universe. And so NumPy and Pandas make it explicit whether you want to do a regular division or a floor division or an explicit two division. Things like power are basically exponentiation. You can see here, oh yeah, if I had two columns and I wanted to exponentiate the price column by one thing and the volume column by something else, I'd want to align the series on its rows, on its index, against the data frame on its columns. Same thing with modulo. Other operations like dot, basically dot is a multiply and a sum, again, index aligned. Operations like your comparison operations, all of them are index aligned. They all just match up something on the index and see is the corresponding value at the corresponding index equal to the corresponding value at the corresponding index, not equal to, or whatnot. They're all index aware operations. If I have two data frames, df1 and df2, align just tells me how they would be aligned. So if I have df1 and df2, you can see align is just telling me what the result is going to be if I try to align these. And so it's maybe like our broadcast 2, our way to peek into what an operation will perform, and I can choose whether that alignment is done only on the index or only on the column, just if I'm curious, oh, if I align these just on the index, what do I get? If I align these just on the columns, what do I get? Dot join is basically taking that alignment and joining two structures laterally, taking the columns of one against the columns of the other. And so it uses the index by default, and it has this L suffix. So if the columns happen to overlap, you can figure out which column is which. I actually don't think that that's a particularly good part of this API, but that's what it is. You can control how that joining is done, just like in SQL. Inner joins, left joins, right joins, outer joins. And merge is just a generalization of this join idea. I don't think the join should take the suffixes. I think what the join should actually be is you take one of the data frames, and you do a set axis to add another layer to the multi-index that is the columns. And that gives you, that gives you this, like that. It gives you one more layer there. You do the other to the other side, then you join them. If you join things with multi-index column axis, you can see it joined nicely, and you can see where the A is and the B is for each of the two sides. And then once you have that, then you can rename what this axis is. So you know, oh, that's the side. The left and the right is the side, and AB, AB, that's the columns. And then you can do group by operations across the columns to explicitly identify, oh, do I want the max of one side, max of the other side? I think that's how join really should have worked. It shouldn't have taken a suffix. It should have created a multi-index instead. Absolute value is obvious. It's just going to take every value in there, and it's going to compute the absolute value. And there's a lot of these operations just perform on every corresponding appropriate numerical value. So abs or clip, they're just going to every value and clipping them by something or absolute value by something. And that's maybe not index aware. Things like min are index aware. They're index aware on the columns. It's going to give you a result that is the indexing for whatever the columns were, unless you specify the index on a different axis, then it's going to give you the indexing of whatever the other axis was. So if you do a min on the column, a min reducing the columns, what you get is the original indexing of the structure and the minimum value going across each column. If you do a min on the index, the rows, it gives you the original indexing of the columns with the min down those columns for each individual column. And the default is usually operating down. Same thing with max. Same thing with sum, prod, and product. Same thing with any and all. Same thing with mean, standard deviation, variance. Same thing with kurtosis, and skew. For median, the same idea. The indexing of this result is going to be the indexing of the axis against which you operated. So if you operate if you operated against the row axis, then that'll be the indexing. If you operate against the column axis, that'll be the indexing. Mode is a little bit different because mode gives you the most common values, and if there are ties, it will give you those values here. Here, this is a range index, but this range index makes sense because that's the 0th most common, that's the first, second, third, fourth, and so far most common value. And so you can see there's a lot of nans and an index align this back together. You can do some very nonsensical things like do a mode on the columns here, but we'll skip that. Count. Just count the number of values on a particular axis, just like min and max. And unique, count the number of unique values. Same thing. Mad, I'm so mad that I didn't realize that the index was what it was. That's what mad does. It reminds you that you should be mad that you didn't pay more attention to the index when you first started using pandas. Value counts. Just counts the number of unique values. This is being done on both of the columns. So this is counting the total number of times each combination, each tuple of each of these columns appear. And so if you look at the index of this, you'd expect this to be a multi-index with the values of the price column and the values of the volume column. N smallest tells you what's the smallest value for a particular column. N smallest 3, what are the 3 smallest values for a particular column? And when I say for a particular column, I mean using that particular column in order to determine, as the predicate, what's the smallest one. So N largest says using the price column, what is the first largest value? What's the third largest value and whatnot? And this is useful, and the indexing is useful because oftentimes it's not the smallest value in a particular column that you want, but what the corresponding value in another column is to something in a particular column. In other words, this line says, tell me what the 3 smallest values in the price column were. And tell me what the indexes are for those. And then look up what's in the volume column. What are the volumes for those 3 smallest prices? This is where the index is helpful. Imagine how much code you'd have to write in order to do this if you didn't have an index and you had to recapitulate the index yourself with a bunch of for loops. It would be terrible. Things like index max and index min, very similar. You want to find what the max and minimum value of that index are, and you're going to use that, then go look up what the actual values are. Things like cumulative min, cumulative max, cumulative sum, and cumulative product just perform operations down the rows. And you can see here, it performed this operation. Cumulative min, it just found the minimum value going down. Now, this isn't particularly useful because you can see it's mixing tickers against each other. There should be some sort of grouped operation where you first group by the ticker and then perform a cumulative min. This should be something like this, group by ticker. And then what you're going to do is you're going to preserve the indexing. So you're going to take this series and you're going to do a series.cumulative min. That's probably what you want, the cumulative min separating the tickers. But largely, you can see this is just a rolling operation. And in fact, those are largely equivalent to just expanding operations on this, except there's no expanding prod. And so it's just an expanding window operation. Talking about window operations, there's also EWM. Again, this EWM, like any one of these other group by operations with zeros operations, gives you something that is indexed by the original structure. EWM is going to preserve the original indexing. Expanding is going to preserve the original indexing. For your operations like shift and diff, just move things around on the index. Just move the data, but keep the original indexing the same. Diff, just move the data, or just do that and perform a subtraction as well. Rolling, just give me 3 windowed values, preserve the original indexing or not, depending on what kind of rolling we do. But no, actually, it'll always preserve the original indexing. It'll always preserve the original indexing because it'll look at 3 rows here, and it doesn't know how to collapse those into a single value. But here's a rolling, another grouping operation. Group by, do a mean that just preserves the index, or it creates the indexing based off what you're grouping by. Group by ag, same thing. This is just a built-in function. This is a user-defined function. Group by transform, preserve the original indexing. Group by transform with an ilock, preserve the original indexing, and then look at what the result is. Group by ag, operate on a series all by itself. Preserve and change the indexing of the result to whatever you're grouping by. Resample. Well, resample doesn't work on this because it's not a datetime index. Resample, telling out what level of that index to use, works. But this is like a group by where you're grouping it by the resampled index. And so probably what you want to do here is something that first groups by the ticker and then resamples in that, preserving the original outer indexing so that you can do further index operations. If you can see from this very tedious walkthrough of almost all of the operations on a Pandas data frame, they all have some relationship to index. They're either index aware, they either operate on the index, they either move data in or out of the index from one of the two indices. Everything comes back to the index in the end. And rather than studiously memorizing all of these operations, it's probably better to understand the rules of indexing and then apply them to the operation that you need to use. And so in conclusion, if we think about why it is that we use pandas in the first place, is it because we have it's a container type that's less convenient and more perplexing than a simple list or dictionary? No, because a list and dictionary can't do what a pandas series or a pandas data frame could do, which is that really nice matching up of things for operations with that additional associated metadata. Is it for the bizarre errors? No, because most of these errors actually kind of make sense when you understand how the indexing works. Is it because we will constantly want to use a dot values to force it to do what we want because we want to constantly do a dot set index? No, because usually if we're doing a dot values or set index, we're doing it because we don't care about the indexing. But if we're aware of index alignment, we generally don't need to do dot values or dot set index that much. It's because we have all these weird, incomprehensible decisions in the API. Sure, things are named kind of weirdly in some places, but for the most part, a lot of these decisions, like the different group by operations, are in terms of how they preserve the indexing. Is it for the minor conveniences? Definitely not, because the convenience that the index provides is a major convenience and is way more valuable than not having to import something like scipy.stats. Is it for the 250,000 lines of complexity that they introduce to our lives as a dependency that could break, that needs to be updated, that we have to keep up to date with? It's a lot of code. This is a big tool and a big project. And using pandas is a big investment into your tools. But as part of that investment, as part of the investment of becoming a pandas expert, understand what the index is all about, understand what index alignment is all about. That 250,000 lines of code is to support this extremely convenient, extremely sophisticated index-aligned operations on single index structures or collections of like-indexed, doubly indexed structures, the pandas data frame. And so why do we use pandas? It is for any of these reasons. Is it for the index? No, it's probably because we have a coworker who wrote 50,000 lines of pandas and then switched jobs and they left us with that, and we're not rewriting that from scratch. That's probably why we use pandas. But if we're going to use it, we might as well know what we're doing. We might as well try to become a pandas expert. Thank you so much for watching this presentation. I hope to see you in the follow-up session where we'll take a look at all of these details and show you how almost everything that happens in pandas can be understood in terms of the index and index alignment. But with that, I'm James Powell. It has been a pleasure presenting to you. Thanks, everybody.